and it's starting now. Excellent, thank you, Sheetal. What I'll just do is share my screen. Now, okay, so today the talk is going to be on quantum teleportation, and I pre-warn you that it is involved. It is a complex issue, although when you think what's happening, it's incredibly easy. Now, there's a contradiction to start the evening. It's actually taking the state of a qubit and transferring that state onto another photon or subatomic particle a long way away. And in fact, as I will mention, the Chinese, this is not a pie in the sky, this is actually being done. The Chinese did it last year from a laboratory, and I'm pretty sure it was Shanghai, that teleported a quantum state to the Micius Earth orbiter. That was a spacecraft actually orbiting the Earth. Around about 1,400 kilometers, I think it went. But the actual, what I'm going to do here is explain it and then do the mathematics of it. And even though what it achieves is exceptionally complicated, because it's basically moving a superposition with these complex amplitudes of alpha and beta across the universe to another point. I might add that it's still constrained, unfortunately, by classical bits, because, and you'll see why with the mathematics, we have to send classical bits to the receiver. So we'll be calling them Alice and Bob. So nothing's happening faster than the speed of light. And well, we'll cover that when we get to it. So I'm going to talk today just about teleportation. What is it? Everybody thinks of Star Trek, of course, and beam me up, Scottie. And in the quantum world, it's a bit different. Although, to be frank, even though it's a long way off, it is possible. You know, if we've already teleported a quantum state, and I think they're very close to doing it for multiple qubits, then it really is just a matter of time before we can, expand on that. But it's obviously a long way off. And then we start talking about what is a human being? Is it just a collection of atoms and subatomic particles, or is there more to it? And obviously there is. I'm going to talk about three things, basically. The no cloning theorem, and I think you're aware of that anyway, most of you there in the audience. It's a case of, believe it or not, you cannot copy and paste on a quantum computer. You have to cut and paste. So, and I'll go quickly through the mathematics of that, why it's contradictory and can't happen. So that's interesting. And then I'm going to create a Bell state, which is basically where the entanglement comes into it, because quantum teleportation is all done through quantum entanglement. And so the Bell state is a special orthonormal state that there are 4 Bell basis states that I'll show you how they're derived and then what you can do with them. how you can reverse them with the classical bits that I mentioned before. The classical bits are sent from Alice to Bob, and Bob will look at those bits and then take, there are 4 options he can take, and he will use them depending on what those bits are, and the bits, of course, are classical, so they're just 0 and 1. But it's the whole reversibility that's exciting. And then the hard part will be, and it is difficult, so please don't worry if you don't grasp it this time. We can go over it as often as you want. But it's the actual teleportation. So what's really happening and how it's done conceptually, and then how it's done in reality. And I've broken it into 2 because the conceptually will hopefully get you in the mind of understanding conceptually the way it works. And then the reality has to be a bit different. But look, let's get into it and see how we go. So teleportation, what is it now? Look, there are basically 3 concepts, if you like, of teleportation. One is just where an object is magically goes through a loophole in the fabric of space-time, and it's seemingly magic. That's not what we'll be doing, but yeah, that's one way it could be done technically. The second way is that every atom, and this is the Star Trek way, every atom of the object is disassembled and then sent to another location and reconstructed. But the way quantum teleportation works is that we scan the object, then we send the instructions for reassembling to another location, who then reassembles it on different molecules and atoms. Now, you may think immediately, and I've heard this on many instances by quantum theoretical physicists, where they say the problem is going to be that you scan in the object, you send the information, and you still have the object, and then the object's reassembled somewhere else. But that cannot happen. That completely contradicts the way of the world, the laws of quantum physics. So get that out of the mind. The original is always destroyed. And in this case, Alice actually measures her qubits that she's entangled in a belt state with Bob. So she measures them, knowingly collapses them, but then because of the reversibility, she can tell Bob, and it's actually, you can do it classically anyway, so you can send it through fiber optic, wireless, or you can actually just call up and say, bit 1 is a 0 and bit 2 is a 1. And Bob will then know the actions he has to undertake. So just quickly with the no cloning theorem, all you've got to know is that you can't copy and paste with quantum computers, quantum computing, quantum physics. It defies the laws, and I'll explain that briefly now. Okay, so imagine that you have a quantum state. Now, you should be familiar with, I'll just, let me, oops. There's a chat, so I use, that's just from Sheetal. Thank you, Sheetal. Come on. I'll just get my annotation out because it's very difficult to know where I'm talking about if I don't. I hate it when presenters don't do this because they quite often say, move this from here to there. And I'm going, where's here and where's there? But now you should be familiar with this equation here. This is psi, and it's the wave function. So a quantum state is, we've got this is alpha and beta are the complex amplitudes. It's the equivalent of the probability. So the chance that the wave, the state is a 0 is alpha, and the chances that it's a 1 is beta. Now, sometimes when they're in, after a Hadamard, they're in equal states. But quite often you may, and these can be complex numbers. So it can be the square root, at the square root of -1. It can be the cubed root of 37 over -42. These can be any complex or imaginary numbers. So it's just like if this was, what's the probability of throwing a heads or a tails, then these would merely be a half each. But you could never have -1/2. So it's like saying you could never have a -30% chance of rain. That doesn't make sense. But in the quantum world, it does. So without any more, I hope you understand this is a quantum state. We don't know what alpha is. We don't know what beta is. We know they are complex numbers. Now, so we don't know the value of psi, but let's say you want to take a qubit in the 0 state and clone it to psi. And this is what we're saying we can't do. You cannot do it. Okay. This is the circuit transformation that we're looking for. So we're going to get psi, and on the first qubit will be psi, and on the second qubit will be collapsed to a 0 state. And what we want to come out of that are 2 psis, so that we've basically cloned psi onto this 0 state. Now, the no cloning theorem tells us there's no way of achieving this, so I'm just going to very quickly introduce you to the math, because it's always handy to know. So what does it actually mean? So here we have a product state going in to a unitary transformation. We want, as I just said in the last slide, we want psi and 0 to go to psi and psi. So we want this unitary transformation to undertake that process. But if we look at what's going in to the unitary transformation, or what would have to go in, we've got psi, which we know is alpha probability of state 0 plus beta times a probability of being 1. That's the first qubit, this one. So for the product state, we multiply by a tensor the second qubit, which is 0. And if we now, and we want to go through the transformation to give us 2 psis, this one and this one. And we need to do it, obviously, we need to do it for all values of alpha equals, alpha and beta from 0 to 1. And that means that we need to have both qubits from being 0, 0, going through a transformation to 0, 0. and 1, 0 going through a transformation, but it has to go to 1, 1 because the second qubit has to be the same as the first qubit. So if beta equals 1, then the second qubit has to equal 1 in order to be, for the cloning to have existed. So now what we're going to do is multiply those tensor products out, and it comes to the Bell state. Now, to cut a long story short, this is not what we want. It's contradictory. This cannot happen. Therefore, quantum cloning is not possible. And it's for this reason. I wouldn't get too hung up on that. I would just make sure you understand why. Now, creating a Bell state is really important. So, let's say...
Eamon, can you hear me?
Oh, yes, I can. Oh, I can hear you now, yes. Is that Sheetal,
okay,
yes?
That's good. Yeah, that's me. Yeah, that's right. On the previous slide, let me see. Was that a proof that no cloning is?
Yes, this derives, if you multiply that out and then reduce it to here, it is a proof.
Okay.
There's another couple of steps that's not really involved there. But I wouldn't get too hung up on that. It's basically showing if it's 1, it doesn't work, and if it's 0, it doesn't work. It can't be, for both of them. So you can't clone it.
Understood.
Yeah. So you can't clone it onto another qubit. This is more important here now. So if we're talking about a Bell state, and that's just and this is where I contradicted myself right at the beginning of the evening, because even though what we're doing is amazingly complicated, look at this. We're only using 2 very standard quantum gates to do this operation. And so what we want to do is get 2 qubits that have been that are in a 0 state, and then we'll put them through a Hadamard and put them through a CNOT. But let's follow it through what happens. So what's the product state before it goes into the Hadamard? So actually after it's it's 0, 0 before it goes in. Excuse me. So after the Hadamard, what is the product state before the CNOT is executed? So here we have the Hadamard. If a Hadamard on the first qubit, as we did last week, a Hadamard on a 0 qubit gives us 1/√2 chances on 0, and plus 1/√2 of being 1. When you do a Hadamard gate on a qubit that's been I can't remember the word, but it's been reduced to 1, then you actually get it's minus 1/(2), 0 minus 1/√2, 1. So, and that's a phase flip, by the way. So that's the difference with using a Hadamard on a 0 and a 1. But we'll get to 1 in a second. At the moment, it's on a 0. So that means it's a plus on the first qubit. This is the first qubit. And then here's the second qubit, which is the 0 state. So now let's have a look at the product state after the Hadamard. And we can see that all we have to do is multiply the 0 ket with into the superposition, which gives us 1 over root 2 0, 0 plus 1 over root 2 1 0. Okay, so that's pretty straightforward. So this now is taken up from the previous slide. Now, if we apply the C naught, and you may remember we had that big matrix for the C naught, but all we have to recognize with the C naught is that if there's a 1 in the control qubit, then it will be flipped. If there's a 0, it goes straight through. So in this case, there's a 0, so that has no effect on the first qubit, but it has no effect. The second qubit remains unchanged. But here, the first qubit on the control qubit is a 1. Therefore, we need to flip the second one, the second qubit. So that goes from a 0 to a 1, which gives us this beautiful equation, which is a Bell state. And that's an entangled Bell state. And if we look up here, it's actually this one here, when the Hadamard and the CNOT gate is applied to 2 qubits and they're both 0, then you come up with what's called the phi plus state. So this is one of the 4 basis states for Bell states, one of the 4 Bell basis states. So if we carry on, and what I've changed here is 0 and 1. So again, this now is a very, very similar process. If you follow the last one, you'll follow this. So now we want to find out what is the product state after the Hadamard. So we've got our superposition that we used to here on the first qubit, because the Hadamard puts it into superposition. And then we multiply it by the second qubit, which is a 1. And multiplying that out gives us 1 over the square root 2, 0, 1, plus 1 over the square root 2, 1, 1. So this is before the Hadamard gate. So if we, after the Hadamard gate, we look at what we had in the last slide, and again, we look at the first qubit, which is the control qubit, and if that's a 0, then we leave it as B. So this one here is a 0, so we don't flip the second qubit. So we leave it as B, 0, 1. However, here we have 1, 0, no, 1, 1, sorry. So the 1 means that we have to flip the second qubit, and we flip that into 0. Now, this is still a different type of Bell state. It is the second Bell state, which is called the psi plus Bell state. And these are really important to understand these states. As I say, once you've done the first one, then everything else just falls into place. So now what do we do if we have the first one is a 0? So the control qubit's a 1, sorry, and the second one's a 0. Same process. So now what we do is take the, multiply it out, it gives us 1 over root 2, 0, 0, 1 over root 2, 1, 0. So that's the product state. When multiply, so here's the product state, and here's the product state here. So when we apply the C naught, the 0 is not going to change, but the 1 will flip it, and we're back to this familiar gate, and that should be a minus there. I must change that because, yeah, that should be a minus, not a plus. Otherwise, it would be the phi plus. But in point of fact, what it is, here it is properly done with a minus, so I apologize for that. And this is called the phi minus state, which is signified by phi minus. And then finally, for the fourth state, where it's 1, 1, and we apply the Hadamard and the C naught. After the Hadamard gate, we've got 0, 1, 1, 1 as the product state. And then when we apply the C naught, oh, I did it again. That should be a minus. Obviously, something went wrong there. So again, it's a minus, but not to worry about that. It's we see that it's minus here, and we have the first qubit to 0, so we leave that alone. And then the first qubit here is a 1, the control qubit's a 1, so we have to flip the target qubit, which is the second one, and we make that a 0. And this is still a Bell state, but it's what we call psi minus. So we now understand what a Bell state is, and we'll see where that becomes vital in a minute. So here are the 4 states, the Bell basis states, and they form an orthonormal basis, which is in a 4-dimensional complex vector that you get with 2 to the n, which is 2 to the 2 with 2 qubits. So it's 2 to the 2, 4, and these are the 4 states. So any questions?
Can I ask
yes.
a question?
Yes, of course.
All right. So in the it's phi minus in that image, phi minus the first ket. Should that not be ket 1, 0? Because your inputs are.
Which one are you talking about? Phi minus. Phi minus here.
Yeah, the first ket that goes in 1 over root 2 times
let's
tensor product.
So we're talking here, aren't we? So we're talking when it's 1, 0.
Yeah. So I thought that the ket, so the bottom left corner there, the ket should be 1, 0 in the product state. Or am I mistaken? Yeah, there, right there. Yeah.
Yeah. No, because when you put, well, let's just go through it. A great question, Sheetal, thank you. When you apply the Hadamard to a 1, let me put my spotlight on. When you apply the Hadamard to a 1, you get the Hadamard in a minus state, but it's still 0, 1, as it is you're
right, yeah, okay. And you've done the tensor product with the ket 0 on the other channel. Yeah,
correct.
okay. And that's where you get 0, 0. Okay.
Correct.
Thank you.
Yeah, pleasure.
Easy. All right.
That's good to sort that out. I mean, it is complex. I mean, you keep on saying, 1/√2, and you just get lost. I've been through this enough to know I get lost. But certainly these minuses are correct, and they were wrong on the other side. So I'll change them as soon as we finish that. Okay. So now this is the difficult bit. Let's go through it and question everything, Cheetal, and hopefully there's no typos, but let's see how we go with this. Now, I say this is conceptually because what we're going to do in the first instance is pretend that it's all in the one laboratory. And so we're going to, in order for narrative purposes, I'm going to talk about what we would do in a perfect world. I'll explain that as and when we get to it. Okay, but Alice wants to send a qubit to Bob, who is very far, far away. So she's got her qubit here with the wave function on, with the probability of being 0 and the probability of being 1. So it's in, we don't know alpha or beta. We don't know alpha and we don't know beta, but we know we want to give it to Bob. And of course, she can't measure them because it will collapse to 1 or 0 with equal probability. So she has to devise a way of sending 2 complex amplitudes, alpha and beta, without measuring them. It really does sound as though it's impossible. And Bob's lab could be on the moon, or at least somewhere we can contact classically. And I just threw this in, but technically, this includes Voyager 1 and Voyager 2. So there's no reason why this couldn't. I'm assuming we have contact with Voyager 1, but actually possibly we don't. We just receive from them rather than be able to get in touch with them anymore. But irrespective of that, it's all, the logic's the same. So again, I'm sorry to keep stressing it, but it's just amazing what we're trying to solve here. We're given a very, very complex superposition to another photon. It can be any subatomic particle millions of miles away. And as I say, this has been done by China last year. Okay, so let's have a look at it. And I think you'll agree, it's amazing.
Sorry,
yes, of course.
One question.
Yes, of course.
You mentioned there, just in that previous comment there, you can give this information to a photon, right?
Yes.
But but with the no cloning, what we're sending are instructions on that photon, as opposed to the complex amplitude, the qubit.
Implicitly, we're sending the complex amplitudes, but the photon that's still on Earth is collapsed, cannot exist in order to be teleported.
But not if we don't measure it.
Oh, well, we have to measure it. We can't do this if we don't measure it.
Okay.
Because that's why it has to be classically in contact. It would be fantastic. And maybe we'll come up with a way, I don't know. But at least at this moment in time, we need to do a classical communication, because the way we do it, I'm just going to go over the, very high level here. The way we're going to do it is by Alice and Bob. You've got the qubit, and then you've got Alice and Bob produce entangled bell states, and then Alice collapses both of hers and tells Bob what they came to, and then Bob, will either do a bit flip, an X gate or a Z gate. It'll change the phase depending on whether it's a 0 or 1. If it's a 1, if it's a 0, magically, this wave function here, if it's a 0, this wave function with these complex amplitudes will just go straight through to the keeper. And if Alice collapses them to a 1, it's not like it's complex. Bob just has to remember on Alice's qubit to do a bit flip, and on the entangled qubit to do a phase flip, a Z gate. And we'll get to that anyway. We're jumping a bit ahead, but I like that.
Sure.
Yes, thank you. So we have 2 qubits here, and on this qubit, so Alice wants to share a bell state with Bob. So she has 1 qubit, which in her laboratory, which has this unknown wave function with the complex amplitudes of alpha and beta. But what she will do is perform a bell state, share a bell state with another qubit with Bob's qubit. So that's the bell state here that we looked at before, and that is shared onto both qubits. Now, Alice performs some measurement on her qubit, the unknown qubit that she wants to the one that she wants to transfer to Bob, and her share of the bell state. So she's going to collapse both of these qubits, like I said before. Now, these 2 qubits are in Alice's laboratory. This one's in Bob's. So when Alice measures the 2 qubits in her possession, both of them collapse into either a 1 or a 0 with equal probability. So you have 4 combinations that it can be. And these are classical bits, so let's call them B1 and B2. Now, because they're classical bits, they can be communicated through the normal channels. Or Alice could literally call Bob up and say the first one's 0, B1's 0, B2 is 1. And then based on what Alice tells him her qubit to collapse to, due to the wonders of quantum entanglement, he can adjust his bell state to go back to the original wave function. Okay. let's sort of see how that happens in here. Now, for narrative purposes, let's assume that they have a quantum channel between the 2. And so they can just perform a bell state by putting in a C0. So you know, so that's how easy that would be. And that's what happens all the time in laboratories throughout the world now. We have 2 bits with a two qubits with a quantum channel, and we put a CNOT between the 2 of them, and they go into a Bell state, and then we can separate them. So here again, let's look at the maths now. So here we have a product state merely multiplying the second qubit with the first qubit comes to the product state before the CNOT. So that's alpha 0, 0 plus beta 1, 0. And Alice can measure her qubit. Now, this is the important thing. I don't know if you guys are aware of the sign basis. There are different bases that you can use to measure the qubit. And so you can have a Hadamard basis or a sign basis. And the sign basis, basically, it's still dead easy. It just has its own way of using plus or minus. And it's orthogonal to the normal Hadamard basis and the 0 and 1. We can go over this again if needs be. Let's just go with the flow at the moment. And we can see that for the first qubit, we have a 0. Now, 0 in the sign basis is written as alpha 1 over square root 2 times with a ket, a plus ket, plus 1 over square root 2 minus ket. And then we've got the second qubit there, and there's a 0. Plus the B11, and again we can see, and it's easy to remember, when you use the sign basis, just as we did with the Hadamard basis, when there's a 1, we change the phase and it becomes a minus here. But everything else is the same. So you should be able to follow that line there. And then when we multiply it through, which I'm having difficulty because of the bottom line keeps coming through. I know there's somewhere I can hide those, I probably should. But if we multiply it through, we get the first qubit and the second qubit, sorry, the bottom line keeps coming in. It's important to realize this. The first qubit is 1 over root 2 plus ket. But the second qubit is what we want. It's alpha ket 0 plus beta ket 1. It's what we want. So the second qubit is what we want. And in the second case where it's a 1, it's what we want, except it's a minus. That's why if it's a 1, Alice has to say to Bob, it's a 1, you must flip your, you must put your qubit through a bit flip, an X gate, to flip it. And we'll see that here. So again, we've got this from the previous, so we can see here we've got it. We've measured it in the sign basis. So we have this equation here, just from the previous page. Now, if Alice measures it and it's a plus, sorry, I said 1 or 0 before, it'll be a plus or a minus, she will have the first qubit will be a plus ket, and the second qubit will be what we want it to be. It'll be psi. It'll be exactly the same as her qubit. And if it's a minus, then the second state is merely applied through a Z gate, which changes that minus to a plus, and then you've got your psi, which is identical to this. We still don't know the complex amplitudes. It really is amazing. All we've done is intelligently use a Bell state and a C-not gate in this instance, and a Z gate. Not hard at all. Unbelievable that we can accomplish this, which we have accomplished in the real world. Now, remember I said, I'll just highlight it, but this C-not gate, this channel does not exist if the guy's up in a spaceship or on the moon or wherever he may be. When you entangle qubits, you do them together. Now, and that can be, you entangle photons through a BBO crystal and then, put them on the qubit, or the qubit is made up of those photons. As we discussed before, what a qubit actually is. And it changes depending on the type of quantum computer, whether it be ion trap, superconductive, etc., but it doesn't matter. All this stuff is the same. So that's pretty amazing. I don't need to go through. Yeah, all I was saying is that this gate doesn't exist. I did that just so that you could see the mechanics of what we need to do. And now all we have to do is substitute somehow that C-not in the fictitious channel. And there's a way of doing that, which we'll discuss now. So once again, this is the total, what we've just been through with the signs. If it's a minus, you've got a minus here, you've got a flip. So this is a summary of where we've been by setting up the Bell state. But as we can't do, always forget my spine. As we can't do, we have to get something to substitute for that C-not gate in the absence of a quantum channel. And the way we do that is, again, ingenious. Alice has the qubit with this unknown wave function on. And let's make that qubit 1. She then sets up a Bell state with Bob. And notice here, so she has this part of it. And Bob has the same thing in his laboratory. But this dividing line here is these two qubits are in Alice's laboratory. This third one is in Bob's laboratory on the moon or wherever. And since she can't apply a C-not from her laboratory directly to Bob's lab, maybe it's a good idea for her to apply the C-not gate to her share of the Bell state. So we'll go through it mathematically in a second, but what she does is she sets up a C-not with her qubit, which is in the Bell state. So there's no channel involved here because it's all in the one laboratory. So let's look at the maths. Let's see what the three states are in, what state the three qubits are in before we get to the CNOT gate. So I'm talking about here. Let's get these product states sorted out before, or for Alice, these product states sorted out before she does a CNOT. So the first qubit is going to be whatever the function is plus times the tensor, the Bell state, because she's got her, it's these two multiplied together. And what do they give us? If you multiply all of this out, you'll get a over root 2, 0, 0, 0, plus a over root 2, 0, 1, 1, plus beta over square root 2, 1, 0, 0, plus beta over square root 2, 1, 1, 1, 1, 1. That's simply multiplying this out. So that's what we've got here. So let's apply the CNOT gate and then see what that comes up with. So with the CNOT gate, this is a little bit tricky. With a over square root 2, 0, 0, 0, it remains the same because the control bit is, I remember this is Alice's, so the control bit is a 0, so no change. And let's move to this one now. So we'll leave that for a second. Let's go to the beta. There's a reason for that. Let's go over beta square root 2, 1, 0, 0. So what that is doing, there's a 1 here, so we need to flip the target bit. And that's this one here, so that goes from 0 to 1. If we go back to the alpha stream again, we have alpha over root 2. Well, the control bits are 0, so there's no change. And then the final one here, beta over 2, square root 2, there's a 1 in the control bit, so the target bit changes to 0. That should be okay. So now what happens, this is the, I'm doing it again. This is the measurement icon. So we've now done that. We've had Bell states between Alice's second qubit and Bob's first qubit. So we've got a Bell state there. We've run a CNOT, and now we're going to measure the second qubit. Right. So again, so instead of doing the CNOT, so when she measures it, what's happening? So the reason why I put those two together is that, so the reason why these two are together is that this is what happens if Alice measures a 0. This is the state that comes through the 0. And here it is here. And what happens? We reduce that to the Bell state, which is exactly what we want. So it becomes alpha 0, 0, beta 1, 1. And it's a plus sign. If we go secondly here, Oh, it's so annoying having that there. I know there's a way I can get rid of it, but never mind. So here with these two here is what happens if Alice measures a 1. And here we can see that we take the 1 out and we reduce it to alpha 0, 1, beta 0, 1, and that should be a minus. I don't know how I've got that wrong. But the important thing, again, let's just talk theory, is we put it through a bit flip. Oh, no, actually, that plus is right. Because all we have to do is bit flip the second qubit to 1, 1. Sorry, so the plus is correct. My bad. So it's that easy. Bob knows what to perform if Alice measures a 1 or a 0 on her qubit. So this is now the total summary. And look how easy it is for the difficult action that we're performing. So there are 3 qubits involved. Alice and Bob are connected in a Bell state. It goes through the Hadamard gate that we mentioned before, and there's a measurement on her actual qubit that has the one that we want to. Sorry. There's a measurement here after the Hadamard. And the Hadamard is the same as if you're measuring it in the sine basis. Just trust me for the moment. So that's just doing it as if you're measuring it in the sine basis. So if she measures the original qubit, if it's a 0, and she will call, actually telephone call, or obviously you can send it in an email or anything like that. But she will say, Bob, it's a 0. He needs to do nothing. If it's a 1, all he needs to do is put a Z gate on his qubit. So the Bell state's already measured. Sorry, I should have said that. So she has to say what both of those are. You can't just say 1. And if she measures her shared Bell state, if it's a 1, if it's a 0, it just goes straight through to psi. If it's a 1, Bob needs to apply an X gate. And we all know how simple that is. We even know the matrix behind it. I think it's 1, 0, 0, 1, but I'd have to check. So by applying an X gate and a Z gate, depending on what her collapse is, that will always come back to that side, that wave function that is here. And that's the power of entanglement. So what have we done? Alice originally had a qubit with 2 very complex amplitudes on, because the qubit was in a superposition state. And we don't know those complex amplitudes. And by merely supplying 2 classical bits, which are either 1 or 0, we have implicitly communicated those complex, 2 complex amplitudes values to Bob. And by doing those measurements, he will come to the same qubit as Alice's original. Wow. Do we have any questions in the chat? Or Sheetal, you can shout out. You're on. I think you're still on audio.
No questions. Just amazement.
Isn't it just? Thank you for saying that, because, yeah, it's amazing. Are you? I know you're probably going to go over it again, are you? Or are you totally with it?
I'm with it. I'm with it all the way to the point where I just need to revisit the math right at the end there, where when you multiply it out, what is happening across all 3 qubits, the relative state changes. I guess it's just literally the math that then
Sheetal,
results in
you're not going to have a problem with that.
Yeah.
You'll be able to see how. Yeah, I mean, I know where you're coming from. You just need to go through the presentation, which of course I'll send you, plus the recording, and then if you've got any questions, please feel free to email them to me, or call me, or text me, or we can have another Zoom, or whatever you want. And you may, if you so wish. I can't remember what I've got down for next week, because this is the 4th. We've got 2 sessions left, and I'm happy to do whatever. I do think it's worthwhile talking about all of the different quantum computer, what exactly is ion trap as opposed to superconductivity, and topological qubit. Now, I think that's a very well worth spent. And then there was one other session that I can't remember, to be frank. So if you have anything you want to cover, now's or during the next week's the time to tell me. Just shoot me a quick email, and we'll go through it.
Sounds good. Yeah, I will have a few questions, I should think, by the time I've re-reviewed this video.
Excellent, not a problem whatsoever. And look, that concludes the presentation. So I'll send you this stuff in the group, and we'll talk, hopefully, because I love your questions. We'll talk and communicate during the week.
Okay. There was one last question in passing. I made a note because I need to learn about it.
Yes.
You mentioned sign basis, obviously extensively there.
Yes.
I was thinking, and my mind sort of switched over to spin, or something like that. Am I in the right ballpark at all?
Yeah. Think of the Bloch sphere, and think of the measurements you've probably been doing so far on the Bloch sphere are the Hadamard measurements. So the orthogonal to them is your sign basis. Look, what I'll dig up a good.
Oh, in the other dimension, so in the opposite of x. Then,
yes.
Okay. So you're just basically reversing the vector to the opposite corner through the center of the sphere, effectively.
Yeah. That's exactly what you're doing. Yeah.
Yeah. So if I'm pointing northwest, I now go to southeast, but in 3 dimensions.
Yes, because the orthogonal. Yes, exactly. That's where it gets difficult to actually show. I know there's a good YouTube explaining that, so I'll get that to you during the week.
If you could, yeah, that would be nice.
Yeah, you'll follow that straight away. It's just the orthogonal.
Yeah, no, it's just relating it.
Exactly.
It's just relating it to the to what you set out in terms of expanding if I recall, the psi function as you multiply that out. I need to look at the video. As I say, you covered an awful lot of material there.
I mean, think about it. Yeah, think about how much was.
I've been taking notes. I have a bunch of notes, but it's nowhere near what you covered off. So
No.
I will definitely need to print off the video.
That's excellent. I'll get that to you sometime tomorrow.
Yeah, looking forward to it. Thank you very much for that.
Thanks again, Sheetal. Talk to you soon.
All right. Cheers, Eamon. Thanks.
Bye.
Bye-bye.